So this is a section on the Earth. We'll do a few sections on it, and I'm just going to give you sort of a general overview. It might be more detailed than you're expecting. Um, so let's move forward. Here we go. So some general Earth facts. You should ask yourself, how big is the Earth, right? Do you know? And the Earth is just a little ball floating in space. Seems big to us. It's about 8,000 miles in diameter. For comparison, the United States is about 3,000 miles across, so that gives you some idea, maybe, if you've traveled much. It's not that big a ball anymore, especially with the kind of air travel we have. It's about 24,000 miles in circumference. Those two numbers are just related by pi. Uh, so the average density of the Earth is roughly 5.5 grams per cubic centimeter, and that probably doesn't mean anything to you, but you kind of have an idea of what density is, right? Iron is very dense or pretty dense. Water is less dense. Styrofoam is even less dense. You look at packing peanuts and stuff like that. And so water is at about 1 gram per cubic centimeter in its density. And rock is about 3, and iron is about 8. And so at an average density of 5.5, the Earth is almost twice as dense as the average rock you pick up on the ground. That tells you that what's down below us is much more dense than what's on the surface. And that's a clue. That's a clue about a lot of things about the Earth. About 70% of the Earth's surface is covered with water. Doesn't have a lot of water below that, but there's a lot, covering the oceans and lakes and things like that. The Earth's atmosphere is about 79% nitrogen and 21% oxygen, with varying amounts of water, argon, carbon dioxide, and other compounds. Water is the most of those, probably. Those are probably roughly in order of composition, although carbon dioxide is actually a pretty low number. Water is usually very somewhere between 0 and 5%, just pushing those other numbers around, so it all adds up to 100 at the end of the day. How much water you have in the atmosphere just depends on how much there is in your area and how bright the sun shines to evaporate it into the atmosphere. The Earth is about 100 million miles from the sun, and so that's a number that we kind of use to measure distances in the solar system. We call that distance an astronomical unit, AU. And so rather than say Jupiter is 500 million miles from the sun, we say Jupiter is 5 astronomical units, 5 AU from the sun. Saturn is 10, Uranus is 20, Neptune is 30, and Pluto, who's no longer in the club, is 40. They're kind of roundish numbers and easier to remember if you do them in astronomical units. By the way, Mars is 1.5, Venus is 0.7, and Mercury is 0.4 astronomical units from the sun. Those are useful numbers. Earth has an active geology and a global magnetic field. And the active geology means, we have earthquakes and volcanoes and just stuff going on and erosion, all this stuff. That sets us apart from planets like the moon. Well, I know the moon's not a planet, but celestial objects like the moon or Mercury, who are basically geologically dead. They have cooled off over time, and there's not much going on inside. The Earth has a hot interior, and so that drives a lot of the geologic activity on the planet. It also has a global magnetic field, which is related to also this activity that's going on inside, which we'll talk about in another time. Here's a slight digression. So there's the general Earth facts. It turns out that the circumference of the Earth was first measured by a guy named Eratosthenes in about 250 BC. And so what he did, this is a nice little picture of it, which I borrowed from the Encyclopedia Britannica, which shows that he was looking at shadows, and he noticed there was a well in Syene that on a certain day of the year, the solstice, the sun at noon shone straight down the well, but on the same day in Alexandria, it made a shadow. And so he measured the angle of that shadow and did a little geometry, a little math, and figured out what this angle was. And since there's 360 degrees in a circle, he figured out how big a slice of pizza this was and how many slices of pizza would go around the planet. And that would be how many times this distance would make up a whole planet. And so he knew the distance between these two cities. it ended up being, this was 7 degrees, so it was about 50 times this distance from the circumference of the Earth, and he was pretty accurate. He got it right within a few percent. And the interesting thing about that is that, Columbus came almost 2,000 years later and couldn't get the answer right. These guys, Ferdinand Magellan, who went around the world, these guys way underestimated the distance they would have to travel to go around the Earth. And this guy, with just some shadows and some math, figured that out. And so he did a few other things that were really impressive in his life. He did a bunch of stuff with prime numbers that computer scientists still talk about in beginning computer science classes today. So you can Google him if you're interested. So if you want to look at the Earth's interior, we call these the chemical layers, and I'll talk about that a little bit as we go. But you've probably known that the Earth has a core, a mantle, and a crust. And these are sort of chemically different. Now, they kind of vary as you go through, but the reason they're sort of described differently is because they have a different chemistry. So as you move towards the center, it gets more dense and more metally. So it's mostly iron and nickel in the middle, and mostly rocks in the outer part, and it kind of works its way through. You'll notice, you kind of see the purple area is the crust. This is not a bad scale drawing of this. The gray area is what they're calling the mantle, and these two areas are the core. The core has an outer core and an inner core, and the outer core is liquid, and the inner core is solid. And we know that by seismic activity. It turns out that we understand how the interior of the Earth works by listening to vibrations. It's almost like doing a sonogram on the Earth, but the sound is being created by tectonic activity, and we have seismographs all over the planet that kind of tell us what's going on. It's very hard to be a geologist because there isn't light coming out of the interior of the Earth. There's just sound vibrations that they have to work with. The crust is a few miles thick under the oceans and 2 to 50 miles thick at the continents. Has a density of about 3. That's what I was saying. It's roughly the density of rocks. The mantle is about 1,500 to 2,000 miles thick. These are kind of roundish numbers. And the density is 3.5 to 5 with metal compounds. So combinations of metals and rock materials, you might say. The core's thickness is about 2,000 miles. And its density is about 10 grams per cubic centimeter. It's composed of iron and nickel. Again, I said earlier the density of iron is about 8, but this stuff is compressed, and so it's more than that. Notice that the crust is the least dense layer. The crust is literally floating on the stuff below it. And we'll talk about that more as we go. This arrangement is a big clue because it suggests that the layers that the Earth may have formed as a liquid. And so the densest stuff falls to the bottom. If you take rocks and throw them in a lake, they fall to the bottom because they're denser, and the lighter stuff ends up on the top. And so we talked about the chemical layers of the Earth. And now let's talk about the physical layers. They're a little different, and so I'm just going to give you a few pieces that we talk about fairly regularly. You can sort of see here this top layer, this little gray layer here, we call the crust. And then below that you can see there are a bunch of layers here, a few layers here that are called the mantle, right? And then there are a few layers below that that are called the core. The chemical composition of these individual layers are pretty close to the same, but they're physically a little different, and I'll explain that. So the crust is pretty much solid. If you dig into the Earth's crust here or in the oceans, it mostly behaves like a solid. Even though all the rocks aren't tied together in a single solid, they're mostly solid rocks. It turns out the upper layer of the mantle is also solid because the Earth is cooling off from the outside in like a potato does. after you've taken it out of the microwave. And so slowly, the outer layers of the mantle are turning into solid rock. They're much more pliable as we go down, and I'll talk about that in a minute. And so the lithosphere, you see this little bracket which has part of the crust and part of the mantle in it, is actually physically all solid, and so it acts like, in many ways, like a single thing. And so it's the combination of the upper layer of the mantle and the crust that acts like a solid, kind of solid rock, and so we often call that the lithosphere. And so that's a physically different layer. There's also a top layer of the mantle, which is pliable and behaves sort of like a plastic, and it's kind of treat it separately also. It's called the asthenosphere. You see it's depicted here in orange, and you can kind of see the bracket here on the left. And so this layer we kind of treat separately. It's chemically the same as the one below it, but it's it acts more, I don't want to say liquidy, pliable. And so it's so we treat it separately also. So the lithosphere sits on top of the asthenosphere. We'll talk about that. So this is just me saying what I said a minute ago. As the Earth cools from the outside inward, the upper mantle solidifies and combines with the crust to make the lithosphere. And so the layer below that, the upper layer of the mantle that's below the lithosphere, is called the asthenosphere. And it acts like a plastic solid because over long periods of time it flows, and the continents float on top of it. So this is a computer-generated image of the Earth's surface, the Earth's crust. This is just kind of a picture of kind of what we see now. The darker blue areas are the deepest parts of the ocean. Dry land is shown in shades of green and brown. Try to depict the ice caps in white, and so on. Kind of get a picture of the Earth's surface. So let's talk a little about what's going on with these continents on top of the Earth. We've all noticed, I think, probably, that some of the continents seem to fit together like pieces of a puzzle. If you remember, Ferdinand Magellan was the first guy who went around the Earth. He went down, these obviously are not right up against each other. Normally somebody has taken them and drawn them this way. So let me just go back a slide. If you look, Magellan sort of went around the globe by following the east coast of South America all the way to the bottom. They had already had maps that depicted the west coast of Africa, and I wonder if he ever observed, Magellan, that this piece fits into this piece. It's certainly, and I think anybody who's messed around with a global map sees that. These continents look like they could fit together, and it turns out they do. And I think a lot of people had observed this over the years. It turns out a German named Alfred Wegener began to publish papers in the early 1920s on this subject, that the continents matched, and that he thought they were at one time together. And most scientists didn't take it seriously. Wegener was a persistent guy, though, and he showed a few things. He noticed that they fit together like pieces of a puzzle. He showed that the geologic strata agreed between the continents. And so if you've ever driven in New Mexico or anywhere really where you can see layers, right? Let me switch over here and see if I can just draw a picture of this, right? You can have a layering strata, right? And I don't know, there might be fossils in here. I'm just making a picture of a fish. This is a rabbit, right? There can be all kinds of different, these might be different colors and so on. Well, what he showed was if you do this on these two coasts, on the west coast of Africa and the east coast of South America, they match. And this was a big clue. Wegener was a persistent guy, and he started going around. And what was interesting was that the farther down you go, the better they match. And so they might not have matched as well up here, right, which is recent stuff that's come down, but they would match very well below, and they would have the same fossils in the same areas once you got below a certain depth. And so he saw that these things were probably touching each other at some point. Or that's what he believed. The other thing he did he wasn't done with, he didn't do just that. It turns out that when things like lava flows, when you have a volcano or something like that, I'm trying to draw South America and Africa, right? If you have a lava flow somewhere, right? Let's say there's a lava flow here somehow. The magnetic field will line up north-south in the metals inside that molten lava as it solidifies. Well, what he showed was if there was a region where these two had the same, there's a reason where they had the same metals in them. In other words, they matched. They were from the same lava flow. He figured he could show that the lines of the magnetic fields matched across that boundary and things like that. There were lots of clever detective work he did to show that that these things not just fit together, but their geology was the same, and the things that happened to them were the same. Where Wegener ran into trouble was he couldn't explain what would cause continents to move across the face of a planet. And nobody had an answer for that. And the physicists at the time, scientists are always trying to shoot down each other's ideas, the physicists tried very hard to think of some way that continents could be moving. They thought, well, maybe if the continents are up a little higher, which they are, maybe the moon pulls on them a little differently than it pulls on the rest of the planet, and that could drag these continents around and stuff like that. Maybe gravity from the sun or another planet. And they tested all these hypotheses, and none of them worked. They couldn't find any reason. So a lot of scientists in other fields said, look, this just isn't possible. But Wegener was a smart man, and he said, well, you just haven't figured out how it happens. It definitely happens. So unfortunately, he died in Greenland doing his work. He froze in around 1950, I think, while pursuing this theory. Nowadays, we have a much better picture of how the continents work and how the plates move. And so what we do on the planet is we put seismographs around and GPSs and things like that, and we can literally watch the planets, the plates. It turns out the Earth's crust has a variety of plates in it, and they run into each other. And so this causes geologic activity. We'll talk about why they do it in a minute, but these plates are rubbing against each other and past each other, and when you do seismology on the Earth, when people put up these seismographs, all of the activity is along these lines. All of the earthquakes and things like that happen along certain lines. We call these the plate boundaries. And so if you look at the epicenter of an earthquake, they're always seem to be along these plate boundaries. And so we monitor this stuff very carefully. You can see here is the west coast of North America. There's a place where two plates are sliding past each other. This is where the San Andreas Fault is in California. There are all sorts of boundaries like this. The west coast of South America has plates that are colliding. This is called a rift zone, where these plates are moving apart and new crust is forming. So there's a lot of activity. Here's another picture. And again, you can see these sort of been broken up into plates. Here's South America on a plate. Here's Africa on a plate. These guys are separating. Whoa! So let's see. So let's look at a side view of what's happening. These plates are moving around. We'll talk about why in a little bit. But here's what happens. If I have like an oceanic plate where the crust is thin and a continental plate where the crust is higher, as they move towards each other, the oceanic plate will get subducted, pushed under the continental plate, and these oceanic trenches occur there. We have oceanic trenches on all these regions around the ocean, these super deep trenches where this is going on. Back in the 1800s, ships captains that were working for governments would measure this. They would drop chains and things like that to see how deep. They'd try to get a map of the ocean bottom, see what's going on the bottom of the ocean. And so one situation you get is these subduction zones where one continent is flowing under another. You can also get a rift zone where two continents are moving away from each other. And here the crust is generally splitting, has to be splitting, and magma will come up and create new crust. This is happening all along the Mid-Atlantic Ridge in the Atlantic Ocean between Africa and South America, for example, but the whole length of the oceans between Europe and the United States and so on. We'll look at a few of these. Dang it. There we go. These are just a few different ways to look at the same thing, and so I'm just going to show you. The causes of these things are convection currents in the asthenosphere and in the mantle. So if you think of the asthenosphere as a liquid, it's not, but if you think of it that way, it's heated from below. The hottest part of the Earth is in the center, and so it's getting heated from below. And when something is heated from below, you get convection currents. The hot stuff sort of rises up and cools off and then circulates back down, and you get these currents in there. Now these are geologic currents. They take a very long time, but they carry heat up, and the material in the asthenosphere actually moves, and since the continents are sitting on top of that, they move with it. And so we have a convection current that's going this way over here that's carrying this oceanic plate to the left in your picture. Similarly, a convection current is happening over here on the right on this picture. It's carrying that plate to the right, and so you get a rift zone in the middle. This is what's happening in the Mid-Atlantic Ridge, where new crust is being created as this region is getting exposed. And so here's a busier version. Let's just talk about a few of these things. Once again, we have a subduction zone here. We have a rift zone here where these two plates are moving apart. And up here, notice these are two sections that are moving apart, but they're split as in a different spot. And so if you look right in the middle here, you've got this plate here moving to the left in the region where the bottom one is moving to the right. This is called a transform boundary or a transform fault. And we were just talking about that a minute ago. Well, more than a minute ago. The San Andreas fault is a transform fault. These guys are moving past each other, not under each other, right, at the San Andreas fault. So here's a rift region, right? Here's a subduction zone. Here's another subduction zone. These plates, this plate can either be stationary, as they point out here, or moving to the right, or moving to the left, right? In either case, there'll be a subduction zone here. The friction produced by this massive continent moving under the other one creates an enormous amount of heat, which often creates chains of volcanoes, like you see along the west coast of South America, where heat is producing magma, which is underground lava, which comes out through volcanoes. You can also get, if you look over in this region here, you can also get just a hot spot in the mantle for whatever reason. Here's another hot spot over here, which will often, if you just get the mantle isn't uniformly hot, and so there can be regions that are hotter than other regions, and they'll just push magma through, and you'll get a volcanic island or something like that in an ocean. And we get chains of islands often that way as the crust moves past. So here, as the crust moves past this hot spot in the mantle, you might get a chain of islands forming as a new section of crust keeps moving by. The Hawaiian Islands are an example of that. It's a series of islands as that continent moves past the, let me see if they show it up in this picture. I don't think they do. No. As this, if there was a hot spot here in this underneath the ocean here, as this plate moves past, it would produce a chain of islands over the top of that hot spot as each new section of the crust moved over that hot spot. And so that's how we get chains of islands sometimes. This, by the way, also recycles rocks. As these rocks are subducted, they get melted and eventually reused, and will often end up back on the surface through some kind of volcanic activity. This picture is an example of what happens when two continental plates collide. Of course, any two plates can collide, and so when you get two continental plates colliding, one must pass under the other, but you get enormously large mountain ranges. The Indian plate is colliding with the Eurasian plate, causing the Himalayan mountain range. Those are the largest mountains in the world, and so that's another thing that can happen. Just another picture. This is a little depiction of a transformation boundary. This is a rift boundary, and this is a subduction boundary. All of these can happen. You can see here's another example of a hot spot in the asthenosphere, which is basically leaking up through the surface and causing an island. And again, as the crust moves past, this one will eventually move on. This little volcano will move on, and another one will form later on over the same hotspot. The asthenosphere isn't carrying this hotspot will often stay in one region as the crust moves past. So sometimes, if a region is stable for a long time, you'll get these passive margins connecting continental crust and oceanic crust. If something isn't being subducted. And so at passive margins, the plates don't move. The continental lithosphere transitions into oceanic lithosphere and forms plates made of both types. A tectonic plate may be made of both oceanic continental lithosphere connected by a passive margin. North and South America, eastern coastlines are an example of passive margins. So that's a little bit about the crust and how it works and how the continents move. Again, we can measure a lot of this stuff just by pounding stakes into the ground with little GPSs on them. The continents move at about the same rate that your hair grows or something like that, just really slow. And so, but over long periods of time, that's a long distance. So seismographs and GPSs are sort of how we monitor this. Geologists are very good at interpreting the information from seismometers. So we'll talk about a little bit more about the Earth in the next section. So here are some questions you should be able to answer. What are the three chemical layers of the Earth? Name two physical layers of the Earth. What's the densest region of the Earth? What's its approximate diameter? How far is it from the Sun? You should be able to answer what's an astronomical unit? Who made the first reasonable estimate of the size of the Earth? What are the lithosphere and the asthenosphere? What is some evidence that the Earth is molten when it formed? How do the continents move? What's a subduction zone? I can think of a few others that I'll put in the PDF version. What's a rift zone? What are these different types of faults? A transform fault, for example. And some questions about Wegener.